Oh, okay. Can everyone hear me okay? Okay. First, MDCW, happy to be here. Make sure I know. Cool. Okay, also in the seminar group, so some of this will be slightly redundant. As a very brief kind of project background to give you an idea of the approach we took and why we made some of the decisions we did. This was a collaboration with, I should say, Pip Ingham and Rachel Moeller at Chevron. We wanted to help them develop specific GC GC-TOFMS techniques to better get comprehensive peak tables of their various petroleum samples. And from that, the straightforward part was just developing relatively straightforward GC GC method. But from that, you have so many more peaks that it really emphasizes the need for a chemometric method to get that comprehensive peak table. And that's the bulk of this talk and the method that we forwarded and recently published on how to do that. Okay, so familiar ground already covered. I'm just going to use this basically to smuggle in talking about our specific setup where, okay, as is pretty standard for petroleum products, non-polar first dimension, we went with a particularly polar second dimension just to try to really get a separation that separated as many peaks as we could, and we specifically used a thermal modulator. Yeah. And here, I mean, again, already covered, as we capture things from the first dimension, we can use our orthogonal separation on the second dimension to separate those analytes. And you can consider it as a kind of unfolded chromatogram, but we tend to use folded chromatograms just for visualization purposes. Okay, so then on to the chemometric method. Just kind of an overview from the start to the finish. One thing to note, we take all of our samples, so we have 3 replicates of each. We run tile-based F ratio. One thing we do that's not generally typical is that we treat the blank as a sample class. So we have 3 replicates of our blank, and we treat it as a quote-unquote sample class for reasons I'll get into in a minute. We do our tile-based F ratio. We get F ratio hit list. Nothing special up to that point, except again for the blank sample class. And then from there, the novel part is that we do a tile-based p-test to try to go from that hit list into determining which of these hits are actually present in which of the samples. And from there, the end goal is to get, we call it a sample-specific peak table. It's just a peak table of, for a given sample, you know, what's in it, like a comprehensive hit list of everything you detected, or peak table, I should say, of everything you detected. Cool. Really quick background, I no engineers covered it. Tile-based F ratio, we specifically did it through chromatography tile. We wanted to have something commercially available. Obviously, any kind of tile-based F ratio tool would also work here. Again, Fisher ratio, difference between the between-class variance and the within-class variance to give you an idea of how analytes change between samples. One thing I want to call out here is that the reason why we used the blank as a sample class is even if potentially, theoretically, one analyte was present in all of our petroleum samples in give or take the same concentration, by including a blank as a quote-unquote sample class, we make sure that there is going to be some variation there so that we can capture it. I should also say that generally speaking, as Renji mentioned, generally when you're looking for analytes that really define differences between samples or sample classes, you discard everything below a given F ratio. And for reasons I'll get into, we did not do that for this. Okay, so our samples, we have 9 different fuels, and again, the blank as quote-unquote sample class. Here, we just use the linear scale as a rough idea of what are the actual bulk components in these fuels. Probably not surprising really to anyone, but we have alkane band, aromatic band. We can see for reference that we have fuels that vary in weight. Some of them have much higher boiling point compounds than others. None of them are particularly heavy. We don't have any diesels, anything like that. And also we have different samples with different amounts of aromatic content. I should also mention that some of these are different batches of the same fuel process, and some of them are different processes. and we just kind of analyze them all together. That's one of the things you can do with the method we propose. So that's the linear scale just for the bulk components. And just looking at this, we see nothing in the blank. And it kind of looks like even on the heaviest samples, we wasted about 20 minutes of our time because there doesn't really seem to be anything in the chromatogram. However, if you look at log scale, we can see that we do in fact have a lot of trace analytes at very low concentration, very late eluting. And because we wanted a comprehensive peak table of each, we wanted to really try to capture those. Relatedly, because we use such a polar second dimension, you can see we have some wraparound here. We did that deliberately. Reason for that is that so long as the wraparound doesn't cause peaks to overlap and co-elute, then it's not really an issue, and we can get more separation on a second dimension in that way. And we can also see finally that the blank does in fact have column bleed, which will be a thing that we get into in a minute. Okay. So the F ratios from our hit list, we end up with 719 hits. Again, we have some very low F ratios. We have some pretty high F ratios. We don't have an F ratio threshold because we're trying to use this as a tool to capture all of our hits. The reason why we can do this is, again, the F ratios are also passing a signal to noise threshold. And that's good reason to take that as grounds to then do our next step, which I'll get into in a second. I also just want to call out really quickly that the F ratio alone for a specific application doesn't really tell us much. We have some very large peaks that might have only a little bit of variation between sample classes. We might have some very small peaks that are present in some samples and completely absent in others. So this is a useful first step, but for our purposes here, doesn't tell us much directly. Okay, so the kind of novel step that makes this method that we're proposing is the use of blank tiles specifically also for p-testing. They were used as a sample class of sorts to make sure that we capture all of our components, but then we can also use the actual specific tiles from our hit list. Generally, the tile is discarded because once you have the pin location, the retention time, that's much more precise. But if you have the tile, you can use it for purposes such as this. Specifically, we take the tile at the blank for the top mass channel, highest F ratio mass channel, and we use that as an idea of what our instrumental background looks like. With that, we infer a Gaussian distribution, and from that, in a given confidence interval, we're able to then, we believe, effectively p-test each of our hits, again, with the purpose of going to, for a specific sample, out of our hit list, which of these hits can we confidently say are actual peaks that are present in this given sample class. For the specific confidence interval, we determine that by taking a specific example, this example here, to try to determine, obviously for this specific example, because we use it to try to determine the confidence interval, we can't necessarily directly trust that. But then by taking that confidence interval and blindly applying it to p-test all of our other hits, we can then be more confident that those are actual analytes in our samples. So here, we can see very clearly we're formate 11, we're formate 18, naphthas 8, 9, FCC gasoline. Visually, we can see we have peaks. They're all the same retention time. We're pretty confident they're there. However, the thing I want to mention is that just by looking at it, there are some other samples where I could see a qualitative argument of whether or not there is an actual peak there. And that's what motivated the p-testing as a way to try to more quantitatively determine which of these samples have this peak and which of them don't. Okay, so with that in mind, if we look here, we have each of our 3 duplicates for different samples. Again, the ones that very visually obviously had a peak, unsurprisingly have a lot of signal at the highest F ratio mass channel. However, if we zoom in, we can see that this is our blank here with a different amount of signal in each replicate. And from there, and from our 99% confidence interval derived from that, we can then have a metric to determine that in naphtha 7 and naphtha 10, we do in fact have enough signal that we feel confident that we can say that this specific analyte is in fact in those samples, whereas in hydrate 11 and hydrate 18, it doesn't clear that threshold. We can also note that we do have some variation between replicates, and we could imagine potentially, and it does occur, in some other hits that we're trying to determine whether or not if they should end up in the peak table, we might have cases where some replicates pass the p-test and other replicates do not. But that turns out not to be a major issue. Out of all classifications of hits, it turns out that only 6.3 of them have disagreement across replicates. In all of the cases, all of the replicates either agree that this analyte should be included or not included based on the p-test. We have just example hits here, a variety of different, we try to pick some aromatics, some different kind of class compounds. And here you can see a few examples where sometimes you have two replicate or one replicate pass the p-test, but in the majority of cases, you either have unanimous failure to pass the p-test or unanimous passing of the p-test. These identifications are a bit tenuous, it's just based on match value alone, but the main idea here is to get at these sample-specific peak tables. And from here, it's a trivial task to just take all of the hits that pass the p-test and put those in a peak table for that given sample class. And so from there, just as a summary of what our sample-specific peak tables look like. Just as a way to kind of emphasize the fact that so many of these are trace analytes, we did very roughly calculate the number of peaks that, if summed roughly, add up to 99% of the total take signal. Just as a point of reference that for each of the samples, around half of all of the peaks in the final peak table are determined to be pretty low in concentration. And we can see here just the number of peaks that end up in our sample-specific peak tables. Unsurprisingly, for heavier samples with more components, we end up recovering more of those. Okay, then to conclude, so one of the things I should mention is that because this is a tile-based system, you get the benefits from that, mainly that you minimize the effect of retention time shifting. It also allows for the recovery of trace analytes without much additional need for user input or intervention. You do, as currently implemented, need to go through the F-ratio hit list, deal with redundant hits, so on and so forth. But this isn't much additional effort on top of that. The method should be widely applicable to different samples. We applied it specifically to petroleum products here, just as part of the collaboration. And also, in particular, any kind of tile-based chemometric approach could be used. If you particularly have samples where multiple replicates are not practical, it seems quite likely that you could use, for example, variance ranking. And as such, you'd be able to repeat this method most likely with your chosen chemometric method, or metric, I should say. Okay, yeah, with that, thank you for your time.